Hi everyone, welcome to our webinar this week. So coming with us today is Nghia Tran from the Oakland University. He is an associate professor there at the Department of Mathematics and Statistics. So before joining the university in 2014 as an assistant professor, he was doing postdoc research fellow at the University of British Columbia. And he got his PhD in 2012 from the Wayne State University I think in Michigan, I guess. And then, this is a pity that, Nghia Tran is an expert in the field of marginalities and optimization. And I think many of us here know him quite well. This is a pity that we don't have him here in Australia, but welcome to Australia and Perth specifically. So now the stage is yours.
Well, thank you, Hoa. First, I just want to say thank you to Hoa and Ben for inviting me to give a talk at the variational analysis and optimization webinar. So today I would like to talk about sub-minima and star minima for a robust recovery. This is the joint work with Fadili at Nobody University and my former PhD student, Nghia Tran at Oakland University. So my talk, we will talk about the introduction of robust recovery, the reason why sub and minimizer is significant in robust recovery. After this one, we will introduce some result with a robust recovery by using sub and star unit minimizers. The next session is about quantitative characterization for sub minimizer. The next one is a group-sparsity optimization problems, and finally some conclusion. So in many different areas of engineering and science, we have a linear equation, very simple equation like this one. We try to solve x naught, but unfortunately we cannot find it. So people make some observations.
Yes, sorry, it looks like we still see just the first slide. Are you changing slides?
I'm changing my slide.
But yeah, we only
you cannot see anything.
Slide.
No,
only
no,
the title slide.
No, it's still the first slide.
Okay. So something wrong with my computer. Just wait me a second. I think I'm gonna change a little bit right now. So do you see my slide right now?
Yeah, it's good now.
Okay, sorry.
It is slide number 4.
I need to share my whole screen, otherwise it. Yeah, so maybe I talk again about the situation that we just have a linear equation, and x naught is a signal that we want to recover.
Can you go back to slide number 2?
Yeah, so number 2 right here, just the introduction. We have a robust recovery. Just the outline of my talk. So for the next slide, we have a linear equation, and we try to solve for x naught. Unfortunately, we cannot easily to solve it. We try to make observation, right, over a linear transformation or sometimes just a random linear transformation. Now the observation cannot be too many observation. So the situation is we have like less observation than the number of the dimension of our signal. So m is much smaller than n. And in that situation, we know that the equation may have like infinitely many solutions. Okay, suppose we can solve it. We can get a solution, but that solution may be not x naught. And that is what we do not want to have. We want to recover exactly x naught. And so in the area of complex sensing, in the last maybe 20 or 30 years, people try to add a regularizer function. So for example, I mean, if they suppose that the solution x naught, it is a sparse solution, then they may use norm 1, the L1 norm, right? Sometimes if we need a low rank function, they may use a nuclear norm or, you know, to solve the optimization tool right here. and get back the solution x naught. And in this situation, I want to generalize the idea that, you know, J naught right here could be any non-negative regularizer. How about D star? D star is also another linear transformation. For example, if we have a gray and white and gray image, and somehow that image, it is not sparse at all, but over some linear transformation, for example, its gradient is going to be sparse. And we put, you know, the D star X right here just for information that over a linear transformation, probably, you know, the image will have some desired property that we want to have. We still have a linear condition right here. So anyway, the optimization problems we want to consider in this talk is very simple like this one. We have a cost function Jx, and the condition is just a linear condition, and we try to solve it. And here is three particular cases that I just mentioned above. We have the sparsity when the J naught function is a norm 1, group sparsity when J naught is a L1, L2 norm, and the low rank situation when the function J naught is the nuclear norm. But when you make the observation, unfortunately, we may have some noise. It really means we may not have exactly, our observation is not phi x naught, phi x naught plus very small noise right here. And our small noise right here is smaller than or equal to some delta. So of course, we still want to recover x naught, but now we have noise. And with the noise situation, people try to consider the following optimization problems. We also still need to minimize the cost function J, but our subject function right now, you know, our condition right now is an inequality condition. Phi x minus y is more equal to delta. And this condition is very close to the situation in the the third equation right here. Now, if the function J is convex, and somehow we can use a Lagrange multiplier to transform problem 4 to problem 5. Okay, so there is some strict connection between problem 4 and problem 5. But anyway, people like to solve problem 4 or problem 5. And then the question is, after solving those two problems, can we get back x naught? And what is the connection between solution of 4, 5, and the previous problem 2? And a state of robust recovery occurs naturally in the following way. When you solve the problem 4, for example, you have the solution x delta right here. And this x delta is very close to x naught whenever delta is close to 0. Another sense is, you know, the solution x delta converts to x naught when delta goes to 0. A very similar situation when you solve problem 5. Any solution x mu right here of problem 5 converts to x naught as well. But you know, we have two parameters right here. We need to choose mu is proportional to delta. Okay. So for robust recovery, you know, there is a very popular result in 2011. It says something like this one. In the case that the function J, our cost function, is a norm 1 function, then x naught is a unit solution if and only if we have robust recovery. Moreover, our robust recovery is have the linear rate in the following sense that the distance between x delta to x naught is a capital O of delta. Okay, and at the same time, x mu minus x naught is also the big O of delta. Of course, mu is a multiple of delta. Okay. In this result, you can see that, you know, the assumption that unit minima x naught is a unit solution is crucial because it's an if and only if situation. So why do we have it? Now, the first thing is it is very natural. You know, you do not want to recover something different from x naught. X delta and x mu, they may converge to a solution to the original problem too. But you do not want that solution is different from x naught. Otherwise, you recover something else. You do not recover exactly x naught. Okay, Now, the second thing is, when X naught is a unit solution to problem 2, it is also a unit solution to the L naught problem. And for this L naught problem, it is, we know there is an NP hard problems. L naught, the norm L naught right here, counting how many non-zero component in X, right? This is a non-convex function. It's very hard to solve. When we have the unit solution for the problem 2, it is also a unit solution for the problem L naught. So what does this mean? It means if you can solve the problem 3 and problem 4 above, you can have an approximation for the problem L naught. Okay, and that is a crucial observation in those 2 popular papers. So there is another result in this direction. Later in 2012, the author supposed that the function J must be a norm. And then they may not suppose unit solution, but they suppose something different. That phi times the norm of phi W is bigger than alpha than W is bigger than alpha than W for all W in the descent cone. And the descent cone is defined like this one. You have a level set like this one, and then you have the cone from X to X naught. Under this, the red condition right here, they show that we also have robust recovery, and the bound is very simple. It's just like 2 delta over alpha. And 2 delta over alpha, definitely it is the big delta. Okay, so we also have robust recovery with a linear rate. Now, the only difference between them is this red condition is not unit solution. And when we read this paper, we wonder, what is this condition? Okay, what is the connection between it and the unit solution? I try to answer it later on, but first I have the observation right here. The descent cone has a close connection to what people call the critical cone in optimization. A critical cone probably is more popular in optimization theory. The closer of the descent cone is the critical cone. And the critical cone is defined this way by using the directional derivative. I just don't want to go into detail. I just want to tell the idea in general. So, but the descent cone is not close. What does this mean? It means the descent cone and the critical cone are completely different. Okay. However, in the case of L1 norm, they are the same. Because in the case of the L1 norm, we can prove that the descent cone is closed. Okay. And in the case, we want to answer where is the solution uniqueness in this result? Indeed, it is hidden in the red condition. Now, the red condition, we can translate the red condition a little bit, and it really means that the kernel of phi intersection with the critical cone is trivial. Okay, but the solution uniqueness could be characterized by using the descent cone in the similar way. The intersection of the kernel phi and the descent cone is trivial. But keep in mind that the critical cone is bigger than the descent cone. So whenever the red condition happens, now this first condition right here happens, definitely we also have the second condition. And so that is the reason why unit solution is not supposed in this theorem, but it is hidden in the red condition. Okay. And here we have a very nice example for the case of a group sparsity when we do not use the norm 1, but we use the L1, L2 norm. We have a very simple cost function. We also have a very simple linear transformation right here. However, we can see that we have the intersection between the kernel of phi and the critical cone is not trivial, but the intersection between the kernel phi and the descent cone is trivial. In this picture, the kernel phi is the red line right here. And the critical cone is look like this angle, And the descent cone is there's the same angles without the boundary. So without this side and this side right here. Okay. So when you make the first intersection, the kernel phi and the descent cone, there is the ray, the red, but it's only the ray, one side of the line. Okay, but this line is on the boundary of the critical cone. That is the reason why the kernel phi intersection with the decent cone, we have nothing but 0. So what does this mean in this example? It just means that we have the first condition right here. Yes, we have unit solution. Okay, as not, it is a unit solution for this problem, but definitely it does not satisfy the red condition that people suppose in the other result. So we want to ourselves whether or not unit solution play important role for robust recovery, and we try to answer this question at the end. So there's still a few questions that I want to answer. Now the first thing is, what does the red condition means? The intersection between the kernel phi and the critical cone equal to 0 means, and why do we need J to be a norm in the other result? And the last one is just what I want to say. Can solution uniqueness sufficiently guarantee the robust recovery with a linear array or not? Probably not. But let's see what do we have at the end. And to answer the first question, we observe the following one. It's very nice. That's indeed the condition right here. This condition, the red condition in the other theorem, is equivalent to the so-called subminima. It really means that the function Jx minus Jx naught is bigger than or equal to some constant c times x minus x naught. And the condition right here, we keep the condition a linear condition. Okay, and this condition, indeed, it is equivalent to solution uniqueness in the case of L1 optimization problem. Or more general, it is equivalent to solution uniqueness for Bolli-Harrow optimization problem. Okay, so that is the reason why, for the case of L1 optimization, there is no difference. Solution uniqueness or this condition, they are the same. They just mean that we have subminima. Okay, so that is the key observation for our research. And after this observation, we wonder, can we generalize the idea to the case of convex function or even non-convex function?
Tran, just quickly, what is the
norm? Yes, go ahead.
So what is the norm in that last line, in that last equation? Is it no?
The
one
last equation right here, just a Euclidean norm.
Euclidean norm. Okay, thanks.
Yeah, but this could be any norm because we only consider in finite dimension. All norms are equivalent. Okay, so we talk about subminima. I just want to introduce the notation again. Now, if we have a function phi, we say we have a subminimizer or x is a subminimizer if we have the following inequality. Right? The distance from phi x to phi x bar is bigger than or equal to c times x minus x bar. The same thing, but it's just for a function, not for the optimization problems. And this I think notation definition was introduced by Polyak in 1979. I think in 1980, at very close time, Crom also introduced the same notation, and he called it as a strong uniqueness, because this condition definitely guarantee the unit solution, especially for convex function. Now, the definition is very local. You can see that it's only true for x around x bar right here. But for the case of convex function, we can extend the ball right here to the whole space. And I just want to say, in the case of convex optimization, it is a global condition. Now, subminima is also very popular in algorithm. People use it to show that a lot of algorithms have finite termination. And the last thing is about subminima is it could be characterized by first order condition using the rational derivative like this one. And we're going to use this one in our paper, but I do not want to go detail about the rational derivative right here. So our very first result is about the solution uniqueness. We try to make the connection between solution uniqueness, subminimizer, storm minimizer. And the first result is very, very natural. We say that X naught is a unit solution if and only if we have robust recovery. Okay, we have the robust recovery if and only if we have unit solution. So in this result, I suppose, we suppose right here that J is a continuous convex function. But indeed, in our paper, we do not need those kind of conditions. But for simplicity, I need to suppose that J is continuous convex function right here. And then you can see if X naught is a unit solution, then any solution X delta will converge to X naught. Any solution X mu to 5, we also have it converge to X naught. Okay, so that is, the reason why unit solution or solution uniqueness is so important in robust recovery. You cannot ignore this one. You must have it. All right. And the first result in the subminima, the main theorem for subminima is the following one. If X naught is a subminimizer to our problem 2, then we have robust recovery with a linear rate. Okay, same thing right here. X delta converges to X naught, and the rate right here is linear. It is capital O of delta. Same thing for X mu. Okay. And this result indeed is called a loss of no result in this area. I mean, roughly speaking, all the results we found in this area about robust recovery with linear rate are covered by this one. All of the conditions they have will guarantee subminima. And in our paper, we also had the precise calculation for big delta right here. And again, the cost function J is not necessarily convex. We do not need convexity for J, and that is very different from the other work. For other work, they work in some specific case for L1, L1, L2, a nuclear node, all of the functions they consider are convex. We do not have the convexity at all. But after this one, we go back to the example 3. In our example 3, as I mentioned, we have solution uniqueness, but we do not have subminima. Okay, but then we recognize that that unit solution is a strong solution, right? So we wonder ourselves, whether or not strong solution also play some important roles in robust recovery. Okay. And the strong solution, strong minima, is defined in a very similar way. Instead, using the order 1, we're using the order 2, and probably strong minima is more popular in optimization, especially when we have to deal with like nonlinear function. We usually have the situation of we have some order right here. Sometimes different order, but strong minima, we have the order 2 right here. And even in Cal 1 or Cal 3, right? We know about this one. When the function phi is differentiable, then we have strong minima whenever the Hessian it is positively definite. Right? And it really means that we can use some second order information to characterize the strong minima. And indeed, it is true because we have the second order characterization right here that iceberg is strong minimizer to 5 if and only if we have this condition and another second order subderivative look like this one. But anyway, just think about the Hessian, right? We have some connection between strong minima and the second order information. So it's very similar. We also have the following theorem. We say if X naught is a strong minimizer, then we also have robust recovery. The rate is bigger. The rate is big O delta to the power of 1/2. Okay, it's very similar result. The proof is slightly changed, but it's very similar. And again, the function J is not need to be convex. All right. And after this one, we go back with our example 3. As I mentioned, that example 3, we have unit solution, but that unit solution is strong solution. So if we try to use robust recovery for that problems, we're going to have the order big O to delta to the power of 1/2. Now the question is, does this remain true for any group sparsity optimization problems? We have a particular case for example 3, but we wonder that whether we have that one for the case of more general group sparsity optimization problems. And I will answer this one at the end as well. So, well, we have a general theory about sub-minima and strong minima in robust recovery. Now, the question is, how can we check those stability? How can we check sub-minima? How can we check the strong minima? And I will, in this talk, I just want to simplify everything. I will focus in the particular case of decomposable norms. I will show that, for decomposable norm, it is possible to check sub-minima numerically. Okay, so what is a decomposable norm? We consider the case, a very simple case where our cost function is just the norm of a linear transformation over X right here. This norm is any norm. Okay, it could be any norm, but this norm gonna satisfy the following condition. We say the norm, this norm to be decomposable if you can decompose the subdifferential into 2 parts. Okay, the norm right here is a convex function, so we also have the subdifferential of the convex function, the norm. We decompose it into 2 parts, right? The first one is over some V, some subspace V. When you make the projection to a subspace V right here, this is a unit vector. All right, it's just a unit vector. When you project any element in this subdifferential to V, it is a unit vector. But on the other side, on V orthogonal, right? On V orthogonal, the projection, the norm, the dual norm of V over V orthogonal is more equal to 1. Okay, and this one is covered 3 main classes, as I mentioned above: the L1 norm, L1, L2 norm, and the nuclear norm. And if you look back, here I've given an example for the case of the norm is L1 norm. What is V? What is E? The unit vector right now is very simple. That is the sign of all the vector UI right here. So if UI is 1, it's going to be 1. UI equals -1. I mean, it's positive or negative, right? We just take the sign. So E probably just like 1, -1, 1, 1, -1, and so on, all over V. And over V orthogonal, of course, is going to be 0, right? And V is Ri, R to the power of I right here. I is the support vector. We want to make sure that, the support vector U bar right here, or UI bar is different from 0. So I is the support set of U bar. So we can separate our space, the elements in the subdifferential into 2 pieces, the V and the V orthogonal. So in this situation, we're gonna have the following theorem. If X0 is a sub-minimizer, if and only if the following condition I happens. Now the first one is the restricted interactivity. So it really means that the kernel phi intersection of the kernel of this linear transformation equal to 0. Now in the case D is identity matrix, right? The popular case D is just identity matrix. This one, it just really means that the kernel phi intersection with V, the kernel phi intersection V equal to 0. It really means that phi, it is injective over V. And that is the reason why people call this condition as restricted injectivity. Okay. Now, when we try to run some numerical resolve for our theorems right here, we recognize that somehow this condition is always true. That is pretty weird, but it's usually true for this condition when phi is a random Gaussian linear map. But the second condition right here is not always true. We call the source identity a source condition. The source identity is rho E. What is rho E? Rho E is the optimal value for this convex optimization problem. Okay, so the first one, the cost function is just the dual norm of A. Now the constraint is a linear constraint. What is N? N is a matrix forming the basics to the kernel 5. Okay, so N is not given. We need to create N. Now the good thing is we can find N easily by using the SVD of 5. So if we have the SVD of 5 right here, N simply come from V star right here. It's come from V star. And after this one, we know that it's a convex optimization problems. We can use some baggage to solve it. All right. So for the case of L1, L2, the group sparsity problems later I will talk about, we just use a CVX optimization package to solve it directly, and then we can get this quantity easily. So, but anyway, even I said it's possible to solve it, it's still a hard problems in some sense. We got to use some package to solve it. Now, the good thing is we can estimate that quantitative, the source identity, by what people call analysis exact recovery condition. And in the case of L1 optimization, they have it already. This is computed in this paper for the case of L1. Okay, and we can show that somehow our source identity is smaller than this identity, tau E. Okay, so what does this mean? It means, if tau E is smaller than 1, then definitely we have a sub-minimizer. In this paper, they only had the following conclusion, that if tau E smaller than 1, you're going to have unit minimizer. Okay, the information we give is stronger. If tau is smaller than 1, we will have sub-minimizer, sub-minima, not just unit solution. So, and and with this, we also have some other identity, but this one probably is the simplest one to compute. Everything is very direct. And the way we check is also very simple. First, we check this tau E. I mean, if tau E is far away, it's very small from 1. So we have high probability that X0 is a sub-minima, right? But if gamma E is close to 1 or even equals to 1, then maybe we are not sure about whether or not we're sub-minima. And then we got to use rho E. So we just want to save our times. We do not use like rho E for any cases, because it's going to take a lot of time to check it. So we use rho E first. If it's not satisfied, it's close to 1, then we got to use rho E to check whether or not we have a sub-minimizer. So the other thing I want to talk is about the group sparsity. We also want to talk about the example 3. As I mentioned a lot of times, that we have unit solution in example 3, but we do not have sub-minima. We have a storm minimizer, storm minima for the example 3. And we try to think about that problems for the general group sparsity problems right here. We have RP, and it is decomposed into Q groups, different groups like this one. The norm, what people call it L1, L2 norm, is the sum of several Euclidean norm, norm 2 right here. For UG right here is on the each space of VG. We decompose it is into like Q groups. VG is just like one particular space. Okay, we also have the dual norms, and the element, the unit vector is defined like this one. It is just like UG over the norm of UG over 2, and we make the direct sum right here as well. So this unit vector is go back to the idea of a decomposable norm. But this one, those notation are pretty technical. Just want to go into the idea of how can we solve how can we determine unit solution for group sparsity optimization problems. And this one is a very nice theorem. We show the following one. We show that if X naught is a unit solution to the group sparsity problems, if and only if it is a strong solution. Okay. So the situation happened in example 3 is not coincident. It is always true. Unit solution, solution uniqueness for group sparsities is equivalent to strong minima. And with strong minima, we can use the second order information to verify it. And somehow we also have another condition right here. This condition looks a little bit scary, but we show later on that it's not difficult to verify it at all. And the M right here, M star is this identity is very similar to rho E. Okay, and if this identity is smaller than 1, we also have unit solution. We also have a strong minima for our group sparsity optimization problems. And I just at this slide, I just want to say, people have a lot of sufficient condition for solution uniqueness. As I mentioned, so solution uniqueness is crucial for robust recovery. A lot of authors provide sufficient condition for solution uniqueness. But because of this theorem, all of the conditions are much stronger than our condition right here. Okay, our condition looks a little bit scary to check, but I will show later that we also can check this one numerically. So there is another corollary. When we have a strong minimizer, a strong minimum, we know that we're going to have robust recovery with the order delta to the power of 1/2. So that is the reason why we have the following theorem, the corollary. Now, if X0 is a unit minimizer to the group sparsity problems, then definitely we're going to have a robust recovery with the order 1/2, delta to the power of 1/2. In this, it's better to say if and only if. But yeah, we have the bigger rate. It's not the linear rate, but this holder rate is also very natural. So now next, I just want to say how can we compute the strong source condition, the zeta E. Now zeta E, we provide with a very scary formula, right? But indeed, it just also an optimal value. Zeta E squared is the optimal value to the following convex optimization problems. We minimize T. At first, the value T right here is so simple, right? And the constraint is just a linear constraint and some other inequalities constraint. Those constraints right here, just a second order constraint, okay? And this algorithm, this convex optimization, we just use CVX optimization package to solve it directly. Okay, we also provide another upper bound for zeta E. And again, the reason we got to do so because zeta E looks pretty complicated. This can be bounded by this value. Okay, and we can find M by using the SVD. One more times, D is given, V is no. So this identity is very easy to compute. The gamma is very easy to compute. All right, so when we check whether or not we have a strong minimizer, a unit solution, we probably check with the gamma E first. And then if it is very close to 1, we're going to go to a zeta E because we do not want to make a lot of computation. So right here, we run about 100 tests. We may need to run more, but the size of the dimension we use, if I remember well, is pretty large. So we only make 100 tests to see the percentage, how many solution will be a unit solution, how many solution will be strong solution for group sparsity optimization problems. So as I mentioned above, you know, the good thing is for 100 tests, the restricted interactivity condition are always true. So we do not need to check that condition. Somehow they are all true. Okay, and then we check the gamma E, the analysis exact recovery condition identity. Only 11 of them, the tau E is smaller than 0.99. It means that, you know, if you want to use the gamma E, it is unreliable. You have 100 tests and only 11 of them is smaller than 0.99. 89 of them is near to 1, right? 89 case is near to 1. And after this one, we have to use rho E, okay? In 89 case right here, we use rho E, and we recognize that 60 case of them, rho E is smaller than 0.95. So we can say that in those 60 cases right here, we have 60 sub-minimizer. So combining those two cases together, we're gonna have 71 sub-minimizer, right? And the other case, we have 29 case when rho E is between 0.95 and even goes to 1.05. The arrow for finding a rho E is pretty big because that we solve an optimization problems. The size is pretty big as well. And then we have, and in those 29 cases, we use gamma E. Gamma E, as I mentioned in the previous one, is, you know, it is direct. Compute is very simple. We can get it directly. And we got like 26 cases, rho E is smaller than 0.99. Okay. Only 3 cases, gamma E is bigger than 0.99. And after this one, we use the previous second order programming. We use the CVX package again to solve the previous, these problems right here, these problems. And then we show that the zeta E, all of them is smaller than 0.95. So what does this mean? I just want to say those 29 cases, all of them are storm minimizer. Okay, so we run 100 tests. 79 of them are sub-minimizer. 29 of them are storm minimizers. And I summarize the idea in this table. Now, some of you may say, that's maybe something wrong. I run 100 examples, random example. How can all of them gonna give us unit solutions? Okay, none of them are not, you know, have like 2 solutions. All of them have only 1 solution. Now the reason is behind what people call exact recovery. Okay, when you choose, you know, phi as a Gaussian linear transformation, somehow you have a high probability to have a unit solution. Okay, those you can look at those 2 popular papers, especially the paper 7 right here, when they consider the group sparsity exact recovery for group sparsities. And our result right here, we just you know, run this the numerical is result right here. Again, we just check the conditions, and we see that, you know, 71 of them are sub-minimizer, 29 of them are minimizers. There is one more thing about exact recovery that I want to say is, you know, as far as I know, most of the result in exact recovery is based on sub-minima. Even they do not know, they didn't say sub-minima. They use the red condition that I mentioned initially. And that red condition is exactly sub-minima. So most of the result on that area, they use sub-minima. How can we use storm minima in exact recovery? is not yet discovered, and we still are working on that direction. So finally, we also have another motivative examples. We talk about the case of L1 norm, L1, L2 norms, the group sparsity example, but probably the most challenging is for the nuclear norm. So we had the following example. That is, we minimize just a nuclear norm, and we have a simple linear equation right here. But then we recognize something like this one. X bar right here, it is a unit solution for these problems, but it is neither star nor sub solution to the nuclear norm minimization problem. Okay, so what does this mean? It means that, you know, unit solution, how can we understand solution uniqueness of the nuclear norm minimization and connect it to the robust recovery is still an open question. Now, the good thing is I think that, you know, they will, instead of the order 1 and order 2, probably we're going to have some order P. Now, in this example, we have the order P, right, there is 3/2. If we are going to the higher dimension, that P may be different. But if we can find that order P, then we can find the rate of the robust recovery. We already know that one. We just do not know that what is exactly the rate when we consider the nuclear norm optimization problems. Finally, I just want to make some conclusion. In this work, we show that sharp, strong, and unit minimizers play significant roles in robust recovery. We can characterize sharp minima numerically. Unit and strong solution for group sparsity are the same, and that is the reason why we can have we can characterize unit solution of group sparsity problems as well. Solution uniqueness for group sparsity is equivalent to the robust recovery with the order big O delta to the above 1/2. There's some direction that we want to work right now. The first thing is we want to work on the nuclear norm minimization. That is a big challenge for us at the moment. As I mentioned, we know that if we know the rate, then we're gonna know the rate for the robust recovery. It's very simple, just like P, if the rate for N and M is B, then the robust recovery is gonna be 1/P. This one, we already did it. Okay, but what is B we do not know yet. I think that there is a paper of Gu Yin and Ting K Pong about this one, but they probably did not answer exactly the same problems. The second thing is what happens when the solution uniqueness does not occur. Of course, initially I say unit solution is crucial because we want to recover exactly the solution, right? We do not want to go to something else. We need to go back exactly as not. But we're still wondering, you know, theoretically, what happens if the unit solution is not a unit? And of course, we got the idea of using weak sub-minimizer or quadratic strong condition or something like that one. And finally, is the final thing that we also want to do in the near future is how can we use strong minimizer, a strong minima in exact recovery, you know, how to recover the image, a signal with high probability when we use the Gaussian or the random transformation. I think that is everything I want to talk today. Thank you for your attention.
Thank you, Nghia, for your very interesting talk. So now it's time for questions. So everyone have questions, just unmute yourself and ask our speaker.
Tran, a very quick question. In the talk, you mentioned several times results and papers, but you didn't you didn't list them anywhere I saw on the slides. Could you just quickly say where the key results have been published?
So for example, I think I did, for example, this one right here. So for example, this one is the key result.
Your results.
My result is right here. Yeah, we are about to publish the paper at the end of this month or at the beginning of November. So we only had the preprint right here, but it's very close date to publish. Fairly, he's keep it, and he promised that he gonna turn it back to me at the end of this month.
Is it available on archive or just?
No, we're gonna publish on archive at the end of the month, and then send to some journal. Yeah.
Okay. Thanks.
Yeah.
Thanks.
Yes. Yeah.
So while waiting for everyone thinking about the
Hi Nghia. First I received a message from Hai here. He said it is the nice work from you, but he has some heart family constraint, and he have to leave. And my question now is, it seems that if you replace in the definition of strong solution, right? You replace the power 2 by P, you also get the result.
Yeah, that's true. The reason we separate sub-minima and strong minima right here, because we want to focus on the situation of the group sparsity. For the group sparsity, we have order 2. But you are completely right about this one. If we have the order P right here,
then you have a 1 over P, right?
Yeah, order P, then the robust recovery will be a 1 over P. And that is what I want to say for the nuclear norm. We think that there is some order P, but what is that P? We don't know yet.
Okay.
If we know that P, we can have the answer for the other open question they have at the end.
Okay. Yeah, but you already have the proof for the.
Yeah, we already have the proof for this one, but we do not put it in it right here because we want to emphasize the idea of group sparsity.
Okay, that's interesting. Thank you.
Thank you.
Can you? Sorry. I would like to see the last example. And
last example, yes, sure.
Yeah, this comments. No.
Right here, yeah.
I think that this is a semi-on-the-big optimization problem. So because S bar is a unique solution, so we have maybe not sub or strong, but we have some P, power P. Yeah. Because
so you mean you already have the result with the order B for this nuclear norm optimization problem? Oh, that's very nice.
Yeah, I think, and it's because this problem has a unique solution.
Yeah. So that's why I say if you have the unique solution, definitely there is the power P over there. But what is P? I don't know. And if you know that should be very nice. I love to talk with you about this one.
Yeah. Moreover, you can choose. Suppose that P is rational number. Rational. P is a rational number. Rational number.
Oh. And so I mean, it does not matter. It's for B, and then the robust recovery will be 1 over B. You know, B is not need to be rational or irrational, but for example, can you tell me what is the rate B you have?
This come from localized with inequalities.
Yeah, I know. They do have B, but my question is, what is that B? Do we know the explicit formula for B for this nuclear norm problem?
I know there is B, and there is, and moreover, we can estimate B, right?
Oh, okay, yeah. So anyway, I think that I need to talk with you more about this one. I know that you wrote a lot of paper in this direction, but I didn't know how to find that P. That is the point.
Yeah.
Thank you.
Okay.
I think you have some minutes for a few more questions. So everyone just ask some questions. Otherwise, I have a very simple question, like straightforward questions. So in terms of not unique, we don't have the uniqueness of the solution. Isn't that, I mean, of course, we don't know what happened there, but can we tell that the sequence converges to a point in the set, say solution set S, and then we can do the minima or weak sharp minima over that set instead of just a particular point?
Yeah, theoretically, we already also proved that one. It really means that. So, for example, if we go back here, for example, you know, let's talk about the storm minima, right? So, if we do not have the unit solution, we replace this condition by the distance from X to the solution set, right? And then we have some, you know, quadratic condition, right? And with that quadratic condition, we can also show the following one, that the distance from X delta, from any X delta to the solution set will be big O delta 1/2. So yeah, I mean, you can use like weak sharp minima, or even you can use like KL equality, you know, to get the order 1/p right here if you want to go further. But it's going to be the distance from the sequence to the solution set. Okay. So yeah, we can do something like that one, but at the moment, in theory, it does look very nice, but we are still wondering the meaning of this one, because as I mentioned, we want to recover exactly the signal X0. We do not want to recover something far away from X0.
I see.
Yeah.
So it is more important to study the set itself, the set itself, not about the like the conversion rate to that particular that solution.
Yeah, the rate is I mean, yeah, we know how to deal with this one now, even we do not have unit solution.
Yeah, thank you.
Thank you.
Okay, so if we don't have any more questions, so please join me to thank our speaker for his interesting talk today. So thank you, Nghia, for presenting in the webinar.
Okay, thank you, everybody.
Yeah,
Thank you.
Have a nice
weekend. Thank you, Nghia.
Thank you.
Bye.
Thanks, bye.
Thank you.